Hi and welcome to quantum field cosmology. In this section, we'll briefly be talking about quantum field cosmology, and then I think we probably will begin with quantum field theory. So, we had the introduction to the course in the last video. Hi, this is Syed Razan, and welcome to course in quantum field cosmology. There was a course introduction earlier, and in which we said that essentially we'll be talking about quantum field theory, not quantum field cosmology. We'll talk about quantum field theory for maybe for 25 lectures, and then initially we talk about classical cosmology for 5 lectures maybe, and then we'll try to understand in physical cosmology that at some point of time it needs a quantum mechanical treatment. Most importantly, there has to be quantum cosmology which has to be used up in classical cosmology. So essentially our talk will be for quantum field theory for next say maybe 25 lectures. And then maybe for the next 5 to 7 lectures we'll have it on this will be dedicated to QFD, and here we'll have maybe classical physical cosmology. And then maybe after this, in the next 7 to 8 lectures, we'll see how this we can develop ideas for quantum field cosmology. So this will be the number of lectures through which we'll proceed on. Then we begin with the course. Altogether from maybe we begin with the course motivation. The motivation for quantum field cosmology is without any doubt the theory of everything. Yes. Well, it's quite ambitious because through quantum field cosmology, we expect a theory of everything. When I say theory of everything, I guess I need to define it mathematically precise. I need to be mathematically precise in defining what exactly the theory of everything will be like. So, maybe. With the theory of everything, we expect to find an equation This could be a mathematically precise definition. It's not mathematically precise, at least a precise definition of what exactly we might be heading towards with the theory of everything. With the theory of everything, we hope to expect to find one simple elegant equation, which by all means explains every known forces in the universe. Okay, with all possible degrees of freedoms in observable and non-observable universe. So this is the definition of the theory of everything, and the theory of everything is the motivation for quantum field theory. When I say it tries to explain all the known forces, we're quite close to it with with all possible degree of freedoms. Again, we are heading really close to it with the field theory. when you ask the question in general, with how close are we with our apparent theories of quantum field theory? Because quantum field cosmology is maybe a sort of a subject which has a few attempts, which has some novel mathematical formulations, which will be introduced through these lecture series itself. So I cannot exactly predict at this point of time how close we are to the theory of everything with quantum field cosmology. But then with quantum field theory, we might be just not one step backward, maybe we are 2 steps backward. Yeah, because what we believe to get to the theory of everything is that we need to have a theory of quantum gravity. Well, this is the holy grail of physics. This is something where enormously intellectual minds have been working on this, maybe for centuries now. But there is we do not have any results. We've got a lot of them. We've got some really strong candidates with quantum gravity. Maybe with we've got things like string theory, which extends with supersymmetry to superstring theory, and then all the 5 branches were maybe formulated together into what's known as the M theory, which was done by Edmonton's maybe genius insight. And then we also have other candidates in the list for quantum gravity, like I can just talk about them. Maybe string theory, which explains the fundamental particles of nature by with say not as particles but tiny vibrating strands of energy. Then we have things like loop quantum gravity. Well, this aims at quantizing space-time, maybe as the hashtag goes, with those strings attached. Brilliant minds like Abash Tecker or Carlo Revelli have been working on this approach. We also have other approaches like emergence theory. A group of physicists from UCLA have been working on this theory called emergence theory. The research group is called Quantum Gravity Research. So this is according to me, quite really bizarre theory, which tries to explain quantum gravity with really different modules. But then, to reach to quantum gravity, I guess we've got a quantum field theory here. So this could be a sort of motivation for the subject. We've got quantum field theory. From there, we expect to go to the theory of quantum gravity. Of course, there are relations between quantum field theory and string theory, but then this is something that we eliminate, going from quantum field theory to string theory. But then we have our own approach here of quantum field cosmology, through which we aim to attain the theory of everything. So this is the basic goal of quantum field cosmology. So essentially, at least for the next, just the way I said, at least for the next 25 lectures, we won't be talking about quantum field cosmology at all whatsoever. We'll only be discussing quantum field theory. And a note to know that when I say it's quantum field theory, all I mean to say is relativistic quantum field theory. It cannot be non-relativistic. It's because if you have things like non-relativistic quantum field theory, of course you have something like non-relativistic quantum field theory. Mathematicians take that up as maybe a stepping stone. When you move from classical field theory, you move to non-relativistic quantum field theory, and then you probably move on to relativistic quantum field theory, which we simply call quantum field theory. Yeah. So what is the point of non-relativistic quantum field theory? It is basically a stepping stone. When you move from classical field theory to quantum field theory. At this point, it's really hard to model any physical situation. The mathematics is quite elegant though, because it's hard to model something because you don't see physical examples of having a quantum system which does not obey relativistic principles. That's because these subatomic particles and fundamental particles execute motion at nearly the speed of light. It has to have a relativistic treatment. So talking about non-relativistic quantum field theory, in terms of mathematics, will only be a stepping stone to move from classical field theory. But then you see, as we go on, we will encounter non-relativistic quantum field theory, but we don't pay attention to it. It's simply because it's not extremely important to modeling physical situations. And the note was simply, when I say quantum field theory, it means relativistic quantum field theory. Now I'll objectively define what the course overview is. because I guess this is really important for you to know what exactly you'll be doing in the next maybe 30 lectures or 35 lectures. So I'm objectively defined. So when I said I have novel mathematical formulations in quantum field theory, which will take us to things like quantum field cosmology, I started thinking, why don't we begin from scratch? When you're talking about quantum field theory, it's quite essential to build up prerequisites properly with classical field theory. So initially, all you're going to see is classical field theory. So we'll spend a good amount of time with classical field theory because you see we start taking divergence from classical quantum field theory lectures in this part itself because we also introduce the concepts of tensor analysis in this way. We sort of take up scalar fields and vector fields and try to merge these fields to get up something like a tensor field, and we'll also have topological analysis of classical fields. So maybe this will run for 7 to 8 lectures. Just after finishing classical field theories, we'll understand mathematically what exactly it means to quantize fields. So once you understand the quantization of fields, maybe we can move on to quantum scalar fields. So quantum scalar fields are the most basic quantum fields that you can talk about. They're mathematically, the most simple kind of quantum fields that you interact with. Yeah, that you need with. I don't know if I have to use the word interact. We talk about quantum scalar fields. Then we discuss quantum Dirac fields, which are also known as spinors. With this, once you're done with quantum Dirac fields, we'll have we'll be quite equipped with the mathematics to move on to interacting fields. So the first interacting field that we talk about is quantum electrodynamics, QED. QED is something that you find in geophysics, and it's the first ever quantum field theory. So quantum electrodynamics talks about interactions between electron field and electromagnetic field. Alright. Then we talk about quantum chromodynamics. I need to put this in the star because it's not quantum chromodynamics that you expect to see in maybe your undergrad or master's level, running into a course program like quantum field theory. This is going to be a bit different. Then we have to discuss perturbation theory. Because you see, the answers that you expect in quantum Dirac fields are quite different to the solutions that you get theoretically out of the mathematics of quantum Dirac fields that we interact with, that we talk about. So we need to use perturbative methods to maybe approximate your answers. Then we have then we've got renormalization techniques. So this is the objective course overview, and this is exactly how it's going to run. So this is objective overview for not maybe quantum field cosmology. I need to say this is objective course overview for quantum field theory. Maybe after this we begin with physical cosmology. With a few lectures of physical cosmology, maybe like the standard Big Bang theory. Then maybe inflationary theory, and then we might talk about places where it simply becomes not negotiable to not take into account the quantum phenomena. So maybe we're talking about the early universe, which is denser and denser and hotter and hotter. And when you go back in time, and maybe that's when your quantum phenomena has become extremely evident, and you need to have a treatment with quantum field theory. So this is a classical maybe an objective for the course. main intention to study is on, in a way, it is simply classical field theory. The lecture series tries to go as deep as it can, maybe in classical field theory. Despite the fact I said it might take up some 7 or 8 lectures, but might move on to maybe 10 lectures, plus 2 or minus. It's more likely that it goes to plus 2, not minus 2. Yeah. So we'll start objectively defining mathematically what exact classical field theory will look like. Maybe I need to define what a field is. So this is a mathematical definition of what a field is. A field phi, okay, you denote a field with a phi. And a field phi is a quantity which has a certain value at every point on the manifold M. So maybe when I say manifold M, most of the times when you talk about classical field theory, you're talking about manifolds. They refer to manifolds with one temporal dimension and three spatial dimensions, which is maybe space-time. Mathematically, you can call it in cosmic space. But then, in our course, we're trying to be as mathematical as possible and as mathematically precise and general as possible. So we might prefer a manifold to be M. So every time I write M, it's manifold with n dimensions and not space-time. Maybe when it's space-time, I will probably define it to be manifold with one temporal and three spatial dimensions. But then again, at this point of time, we need to be again precise with the definition of what a manifold is. So I won't write down the definition. I just okay. Maybe I need to write it down. I write it down here. Manifold M was a topology with space distributed, which locally resembles an Euclidean space. We understand topology that spaces might stretch and bend and turn and twist and all these sorts of things happen in space. Unlike the case in geometry, where you need to work with maybe solid or eternal space. Whether you understand a manifold to be a topology with space, which at every point, maybe locally at every point, which resembles a Euclidean space. And then we have again a mathematically precise definition of what Euclidean space is. So I don't think we need to discuss any more on that. Maybe we can have a fields even on some complex fields like maybe Hilbert spaces. So now we come up to an even more mathematically precise what a classical field is. By definition, we understood that a classical field phi is a mapping from a manifold to what we call S. This S is called bracket space. At this point, we understand that despite the fact that quantum field theory itself is not a very mature theory, maybe as the saying goes, you pick up a calculus textbook, maybe a calculus or a linear algebra, or for that matter, a classical field theory textbook, which was maybe written 100 years back, and then you take up a textbook which is just published, you don't see any difference in the content or any difference in the objective of the text. Maybe there might be a difference in the way of presentation or the approaches taken to solve a problem, but that's not the case in quantum field theory. Quantum field theory is not a mature theory. Okay, it depends on the kind of mathematics, on the kind of rigor that you go with, and that's quite different with mature theories. But that's not the case in classical field theory. Classical field theory, as I gave an example, is one of the best examples for a very mature theory. This is a very mature theory. It's mathematically defined, and it's got a lot of rigor. Okay. Whereas you see, quantum field theory is dubbed to be non-rigorous, but then we try as much as possible to include a lot of rigor. So this is a definition of a classical field. The classical field is mapping from a manifold to a target space. Now, what does the target space belong to? That can possibly belong to anything that you want, and depending on what the target space belongs to, you name your field. Maybe we can begin with a few examples of what the target space can belong to, and then name our fields. Maybe I can talk about as cases or examples. For example 1, when your target space belongs to real numbers. So what happens when your target space belongs to real numbers is that your field phi, which is the position of which is a function now, is from a manifold to real numbers. So in this case, if phi is called a scalar. So example 1 is when your target space belongs to reals, your field is called a scalar field. I hope you've seen a lot of scalar fields. Maybe what you can use to model scalar fields. Maybe you can model things like densities, temperature, and there can be a lot of physical situations which you can model using scalar fields. These are the concepts of fields that we see in terms of abstract algebra, not physically. Okay, these are not physical interpretations. These are things that you see about fields as elements of abstract algebra. You've got elements in abstract algebra like groups, rings, fields, vector spaces, and modules. So these are fields from the topic of abstract algebra that we're talking about. So you can also model any physical situation where you've got a field, where you've got a field which is just represented with real numbers. We move on to example 2. These are classical examples of how the electric series proceed about. So if you have your S belonging to maybe a vector bundle, then you can talk about your field mapped from M to Rn. So Rn is a vector space. So this is example 2 where these kind of fields are called vector fields. The next very obvious example comes up with gauge fields, but then we don't talk about gauge fields at this point because we might proceed about in a different manner at this point. You'll understand this. Maybe you can have a lot of examples. What I said also is simply restricted with your ability to have it to a sample of elements. So example 3, you can have your S to be S squared, maybe where this S is the surface of a sphere. This is called the sigma model. There are a lot of examples which we can maybe talk about later, because now we involve ourselves to maybe generalize the two very known forces for fields we know about. We talk about scalar fields, example 1, and we talk about vector fields, example 2. We also know mathematical objects which sort of classify and generalize these two things. There are mathematical objects called tensors, which I hope you've guessed, which sort of links between scalar fields and vector fields. So we call them Tensor fields, and apparently of course is taking a diversion from not just using a vector analysis and vector operators to talk about vector fields and scalar fields. We take about a diversion into what we call tensor analysis. So we talk about tensor fields, and all the notations that we talk about is the notations of tensor analysis. You might say, what causes us to generalize the scalar fields and vector fields to tensor fields? It's not just a point of generalization, but then we see there are a few loopholes in vector fields, which I expect to show you. So those loopholes in the vector fields are sort of we overcome them with tensor fields. So apparently we're going to understand tensor analysis so that we can talk about tensor fields and then generalize our target space to tensor space so that we can have tensor fields instead of scalar or vector fields. But then before beginning with the tensors, I expect you to know the vector operators. I'm sorry, I forgot to say the things that can be modeled with the vector fields. So the things that can be modeled with vector fields are fluids. So you can model fluids. I guess the best way to model fluids is by using a classical field theory, and especially with vector fields. And it's just because it's great to assume water to be a continuum rather than examining the number of particles it has. Of course, you cannot treat the interacting particles of maybe in order of 10 to the power 23 because it's just ridiculously complicated in that case. So you got something like to model maybe scalar field, to model fluids, you need to take up a classical field theory, and maybe you can use vector fields to model fluids. And then you got classical electrodynamics. We've got classical electrodynamics, the standard of which is simply taken up by Maxwell's equations. So you talk about Maxwell's equations in terms of maybe vector analysis. So of course, classical electrodynamic field is gauge field, but I'm talking about Maxwell's equations which I described in that way. So there are other physical examples. In fact, there are maximum physical examples of modeling situations by using maybe you can monitor currents. By currents I mean maybe wind currents or water currents with turbulence can be modeled easily with by fluids I mean is it might include in that case, but yes, that's how you can have a lot of physical situations which can be modeled by using vector spaces. So how exactly a vector space looks like is something like maybe you can have your vector space, and which at every point maybe is represented with a vector pointing in a certain direction. So this is the best to model fluids. Maybe something like this. So you got a field belonging to a vector field. Maybe in this case you work with non-linear partial differential equations as well, because that's the thing that you need to use. That's the correct aspect that you believe can be used to understand fluids as perfectly as possible. If you want to solve the Navier-Stokes equation in fluid mechanics, you need to have with non-linear partial differential equations. Well, I hope we also have a class of non-linear partial differential equations where we have approaches to solving the Navier-Stokes equation. That's one of my favorite problems. I think we can talk about classical that's Newtonian. We can talk about Newtonian classical gravitational field. We can talk about We can talk about statistical mechanics and maybe fluids. The description of these things with the approximation of classical fields is just amazing, because you see the approximations that we get to analyzing these situations by using the classical field is really very close to what we can expect with a quantum field. You add decoherence to it, and you overcome the scale factors of you having larger scales and smaller energies will give you almost exactly the predictions that we have in classical field theory. And I guess that has to be the point of studying the classical fields. Maybe at this point I can explain to you what makes us choose something like classical fields. So maybe you have a quantum field, okay, and then you move to quantum fields with quantization from classical fields. So if this is where you scratch, this is where you're starting from, maybe from scratch, we go from classical fields to quantum fields. It has to be a reverse process as well. So what happens is, maybe it's a natural question that why did we begin with classical field theory for these situations and not just directly from quantum field theory? So it has an excellent answer, because the classical fields are just beautiful and elegant at binding situations like these, and these are the situations that we first interacted with. It's just because you're naturally inherent to these kind of situations, maybe like the world that you're living in has these you can call them limitations of large scale and low energy. The world that you live in has these factors, these limitations of large scales and low energy. The large scales, I mean, these are the scales where quantum phenomena are not evident. You don't end up, seeing things like Heisenberg's uncertainty principle or superposition principle in your day-to-day life, right? So, by that, we have a limitation of large scales, that is, scales in which quantum phenomena are not evident, and low energy. By low energies, I mean, maybe you don't take into account relativity phenomena as well. We have a clear distinction about lower energies, that is, when you tend to go at the speed of light, at least closer to the speed of light c, which is 2979458 meters per second. That's when relativistic phenomena begin to become really evident, but then you don't actually have a scale factor of where exactly distinguish between quantum phenomena and classical phenomena. You don't know that exact boundary after which you have classical treatment and before which you have the quantum treatment. Of course, when you're talking about smaller things, I mean you're understanding the interaction between atoms, and maybe you can have approximation to an angstrom, 10 to the power minus 10 of a meter. So maybe at that scale you have quantum phenomena which are extremely limited, which takes us to the fact that you have to have a quantum mechanical treatment for these cases. And of course, there's another limitation, that is the presence of decoherence. So we have a dedicated lecture on decoherence. So of course, one lecture will never cover the essence of decoherence, but then we try as much as possible to brief decoherence. So these are the limitations under which we start modeling these things in classical fields. So from classical fields, maybe you remove decoherence and you quantize the fields, you go back to quantum fields. So your theory, your mathematics will be really elegant enough to go back from the quantum fields to classical fields with addition of decoherence, and when you add these limitations of large scales and low energies, you get back to classical fields. Alright, so this is how classical fields are modeled, and this is their basic structure. Maybe I can say we're done with the kinematics of the classical fields. We understand how these fields are, how mathematically these fields are set up as this is a setup of a classical field. Maybe we can talk about how these fields interact and what we can use, what are the physical situations that we can use to model these fields. With maybe we can begin with vector fields. These scalar fields are really simple, because at every point your field is assigned with a numerical value which is a real number. So we might begin with vector fields, then you start analyzing the properties of fields and how these fields interact. Then you have a generalization to tensor fields, in which we begin with altogether beauty from tensor analysis. Alright. Vector fields, but at least I can call it analyzing vector fields. we've got two operators which we require at least. So lambda or del, with which you can have, maybe if you have a vector bundle is this, and then you've got something like, this is called the gradient. This is divergence. Curl. These are the three operations that you can do with vector operator of lambda. That's gradient, divergence, and curl. And then maybe you also have another operator called Laplacian. So you can have a scalar Laplacian and a vector Laplacian. These are the operators I hope you know. And so if you're talking about vector fields, I can probably finish talking about vector fields with, we can maybe end our discussion of vector fields for this lecture with Maxwell's equations. When we talk about vector fields in Maxwell's equations, and we talk about vector fields in fluids, at least at the first part of the course. And then after this we move on to tensor analysis. So I guess this is how it will run. Maybe in the next lectures we can talk about Maxwell's equations and fluids, which are just extremely good with the use of vector fields to model these equations. So you can talk about Maxwell's equations and fluids in the next lecture, and then move on to the generalization with the scalar fields and vector fields to tensor fields. Maybe I'll just write down Maxwell's equations. With this being the first one, which is Gauss law, we also write the integral forms of Maxwell's equations. And so these are Maxwell's equations. We'll write it in integral forms as well. And the next lecture we'll talk about Maxwell's equations and fluids, which are used with modeling vector fields. Thank you.